Hello, this is Team Yarn. This is our jet pump for our fluids dissection project, and the use case for this is in a deep well or a sump, and there's some key parts that you can look at for our dissection. So we'll start off with the radial intake screen. This is the intake for the water, and it's in the form of a radial impeller that pushes the fluid on the sides, but it has an intake screen just to stop any debris from getting inside of the pump. And it has stacked impellers and diffusers. If you look over here, it has stacked impellers and diffusers that we'll discuss more on later. But each stage of these is going to increase the pressure in the pump as the water moves along. And it's also got a rotating shaft, if you look inside here. And the rotating shaft is driven by an induction motor, which I'll display the specs on the screen for shortly.
All right, cool. This is a quick breakdown of how we took this apart. We used a reciprocating saw to pop this open. We used a bunch of WD-40 wrenches, impact wrenches, nuts, etc. to get everything out separated from here. In this stretch of two, there's a series of impellers and diffusers. We have a diffuser right here, impeller, and then impeller, diffuser throughout the whole length of the system. The diffusers help create an axial flow between impeller stages. Pressure increases with each stage pushing the liquid up, and then the centrifugal force that pushes the fluid radially outward is caused by that negative, or that lower pressure region caused by the impellers. Here we have a check valve to prevent water shock. When there's a lot of fluid moving and it stops suddenly, it'll kick back and they'll harm the motor and the system overall. This check valve right here prevents it, or at least mitigates it.
The main governing principles of our system are conservation of mass, conservation of angular momentum, and conservation of energy. So starting off with conservation of mass, obviously this is really important because we want flow in to be equal to flow out. We want the flow rate of each stage to be equal to each other, so we want the flow at each impeller and each diffuser to be the same. This becomes really important because if you look here, we want, in the stage of the diffuser, we have gradually expanding passages. When we exit the impeller, the fluid is high velocity, and then it enters the diffuser. We want the high velocity, low pressure fluid to become low velocity, high pressure. And so, based on the conservation mass, area increases, velocity decreases, which brings us to modified Bernoulli equation, or the ideal Bernoulli equation, which relates potential energy, kinetic energy, and pressure energy. And so, if we're decreasing the kinetic energy that was found in the initial fluid from the impeller's exit, then we're going to increase the pressure energy. So now we're not using the ideal version of Bernoulli because ideal version of Bernoulli does not account for head added from mechanical machines or losses from friction or turbulence. So this is basically just saying that we are adding mechanical energy and we're decreasing losses from friction and turbulence. So energy in is equal to energy out plus losses. Then we move on to conservation of angular momentum, and this is derived from conservation of angular momentum, which basically just says that the head from the pump comes from the change in momentum that comes from the impeller. Here we have other servo machinery equation. This comes from the conservation of angular momentum, where it says that you can calculate the head added from the pump by looking at the change in angular momentum given from the rotating impeller. We then move on to multi-stage addition of head. This just says that the number of stages times the head added from the pump gives us the total head. Each impeller adds head, which is why we want a longer pump instead of a wider pump. We then move on to Reynolds number. This is pretty universal. This just tells us whether or not we have laminar or turbulent flow. For our purposes, we want turbulent flow so that we can maintain a attached boundary layer and we can have more efficient pressure recovery. We move on over here. We have Darcy-Weisbach. This helps us figure out how we're going to design our system, specifically the length of the pipes, the diameter of the pipes, roughness. Here our frictional coefficient is determined by Reynolds number and the roughness of the pipes. This tells us whether or not our head added by the pump can overcome the frictional losses given by the pipe system. Really important. We move on, we have our pump curve system curve intersection. This helps us identify the operating point of the system. We want our flow rate to be determined by the system, not the pump, so they need to work in collaboration with each other. We move on, we have brake horsepower, which is just the power in the motor, the power given to the pump by the motor. Our water horsepower, which is the power given to the water by the pump. And our thermodynamic efficiency, which is just the amount of electrical energy used to actually pump the fluid and not lost to heat or any additional frictional losses. Okay, great. So first we have our geometric calculations. What we want to do first is calculate our flow area. Our diameter was 1.5 inches, which converted to meters is 0.0381. We use this equation to solve for our flow area, which then we can use in our exit velocity equation we got from conservation of mass. Using that exit velocity and an assumed approximated 10 gallons per minute for our volumetric flow rate that we identified from charts from Franklin electric motors, we then proceed to calculate our Reynolds number using density of water, friction coefficient. This gives us a Reynolds number of 2.1 times 10 to the fourth. Having magnitude of 10 to the fourth means that this is a fully turbulent flow, which is really good for pressure recovery. We then move on to calculating our brake horsepower. We don't need to calculate this because it was given by the tag for Franklin Electric Company. We just use the given 3/4 horsepower times 1 horsepower, which is 7.6 watts, and this gives us 160 watts. We then move on to calculate the head capabilities based on the motor. We have a rated shaft power of 560 watts as we found here. We have an assumed efficiency because we can identify all the unknown variables, 60%. And then we just calculate the power, the water horsepower, and then rearrange that equation to solve for the head. We then get a capability of 177 feet. Okay, so why this design? This design is best suited for low viscosity, high density liquids such as water, which it currently uses. We use pump similarity laws to identify the most efficient and optimized parameters. We have flow rate law, head law, and power law. Obviously, the most pressing proportionality is the one between power and diameter. This has a power of 5. This is incredibly important in identifying like how much bigger you want your diameter to be. We can't optimize flow rate and head and then increase power by so much that we need a bigger motor. That's why our current design is the most efficient. It's a long pump, it's thin, not wide, and it just utilizes the numerous stages of impellers and diffusers to increase the head gradually, as opposed to having one big impeller with one huge diameter.
So obviously we're going to take a lot of losses to the environment, but the main goal about the system is that we want to match the optimum performance of the pump to the system it's driving. And this is because the pump alone does not set the flow rate, but rather the system does. So an example of this is we're using water for this pump, but if we use a more viscous fluid like syrup, we're going to have a lower Reynolds number and we're going to have higher friction. A lower Reynolds number means we're not going to have less turbulent flow, and turbulent flow is required to keep the diffuser boundary layer attached and allow efficient conversion of velocity into pressure. And if the diffusers can't work properly, they're going to fail. Not good. Pump's not going to work. And if we're using air, density and pressure are going to go down. It's basically just going to be a weak fan. The pump was not designed for air, it's designed for water. But as I said before, the pump alone does not set the flow rate. The flow rate is set by the intersection of the pump curve and the system curve. And the pump curve shows that the head decreases as the flow rate increases, while the system curve shows that the required head increases with flow rate due to friction losses. The operating point occurs where these two curves intersect. Increasing the pipe length, reducing diameter, or closing a valve shifts the system curve upward and lowers the flow rate, and reducing resistance increases the flow rate, even though the pump itself has not changed.